Hello and welcome. Tonight we'll be exploring one of the greatest mysteries in modern space exploration, the search for water on the moon. At first, that idea might sound almost ordinary. After all, we often hear news about water being discovered somewhere in our solar system. But the moon is different. It has been our closest celestial companion for as long as humanity has looked up at the night sky. We have walked upon its surface. We have brought pieces of it back to Earth. We have studied it for generations, and yet one of its most important secrets has remained surprisingly difficult to understand. It is a mystery that stretches across decades of exploration, countless scientific debates, and missions launched by many different nations. More surprisingly still, every time scientists believed they were finally close to an answer, the moon quietly offered another question instead. So, find a comfortable place to rest, settle into a peaceful rhythm, and let's gently begin our journey into one of the most fascinating scientific puzzles of our time. For much of modern history, scientists were almost completely certain that the moon was dry. It seemed like a perfectly reasonable conclusion. Unlike Earth, the moon has almost no atmosphere to hold moisture close to its surface. There are no rivers winding through valleys, no clouds drifting overhead, no rain falling onto ancient mountains. During the long lunar daytime, sunlight shines relentlessly onto exposed rock, heating some regions to well over 120 degrees Celsius. Without air to protect it, any exposed water should quickly escape into space. Everything appeared to support this simple picture. The moon was beautiful. The moon was ancient. The moon was silent. But above all, the moon was thought to be dry. When astronauts from the Apollo missions returned home with boxes filled with lunar rocks and dusty grey soil, scientists examined every sample with extraordinary care. These precious materials had travelled nearly 400,000 kilometres to reach laboratories on Earth. Every grain carried clues about the moon's history. Some researchers noticed tiny traces that hinted at the possible presence of water. But the amounts were incredibly small, so small that they were almost impossible to distinguish from contamination introduced after the samples returned to Earth. It seemed much more likely that a little moisture from our own planet had accidentally mixed with the lunar material during handling. The simplest explanation usually wins in science, so the conclusion remained unchanged. The moon was dry, or at least everyone believed it was. Then, several years later, another mission quietly added an unexpected clue. In the 1970s, the Soviet Union launched a robotic spacecraft known as Luna 24. Unlike earlier missions that mostly collected loose material from the surface, this spacecraft drilled nearly 2 meters into the lunar ground before returning its samples to Earth. When scientists examined those deeper layers, they found something surprising. The soil appeared to contain about 1/10 of 1% water. It was an astonishing observation. Even more interesting, the deeper the drill reached, the more water seemed to appear. Yet this remarkable discovery changed almost nothing. Most scientists remained cautious. Once again, contamination from Earth seemed like the safest explanation. After all, extraordinary discoveries require extraordinary evidence, and one unexpected measurement was simply not enough to overturn decades of scientific understanding. Looking back today, there is something quietly beautiful about that moment. Science is often imagined as a collection of sudden breakthroughs, where one discovery instantly changes everything. In reality, it is usually much gentler than that. New ideas often arrive softly, almost whispering rather than shouting. They wait patiently while better instruments are built, more observations are gathered, and confidence slowly grows. Sometimes the evidence arrives years before people are ready to believe it. The moon continued to keep its secret. For almost 2 more decades, the question rested quietly in the background. Then, in the 1990s, technology began asking questions that previous generations simply could not. Rather than looking only at rocks collected from a handful of landing sites, spacecraft started examining the moon from orbit, seeing the entire world as a connected landscape instead of isolated locations. One of these spacecraft revealed something unexpected near the lunar South Pole. There were enormous craters whose floors had remained hidden from sunlight for unimaginably long periods of time. Imagine standing at the bottom of a deep valley where sunrise never comes, not tomorrow, not next year, not even after millions or perhaps billions of years. The sunlight simply never reaches you. These places became known as permanently shadowed regions. At first, they seemed like little more than geographical curiosities, but scientists quickly realised they might hold the key to an entirely different story. If sunlight had never reached those crater floors, perhaps temperatures there had remained unimaginably cold throughout the moon's history. And if that were true, perhaps water could survive there. The idea felt almost impossible. The moon was still widely considered a dry world, yet suddenly scientists had found places where the impossible might quietly become possible. It was rather like discovering an ancient cellar beneath a desert house. Even though the scorching heat outside had baked the land for centuries, hidden beneath the surface there might still be a cool room where delicate things could survive untouched. For the first time, researchers were no longer asking whether the moon had once been wet. They were asking something far more intriguing. What if tiny pockets of ice had been hiding there all along? That single possibility transformed the search for lunar water. No longer were scientists searching everywhere. Instead, they had a destination wrapped in permanent darkness. A place so cold that it challenged everything we thought we knew about our nearest neighbour. And as more spacecraft prepared to investigate those mysterious shadows, the story of lunar water was only just beginning to unfold. The answer, it seemed, had never been waiting out in the bright sunlight. It had been quietly hiding in the darkness all along. The possibility that water might exist on the moon was no longer quite as easy to dismiss. Tiny clues had begun to appear, scattered across decades of exploration like faint footprints in fresh snow. Yet even if those clues were genuine, an even larger question quietly emerged. Where could water possibly survive? The moon seems, at first glance, like one of the least welcoming places for something as delicate as water. During the long lunar day, sunlight pours directly onto the surface for nearly 2 Earth weeks without interruption. There are no clouds to soften its warmth, no atmosphere to scatter the light, and no gentle winds to carry heat away. Bare rock simply absorbs the sunlight until parts of the surface become hotter than the inside of many household ovens. Then, just as gradually, the long lunar night arrives. For another 2 Earth weeks, darkness settles across the landscape. Without an atmosphere acting like a blanket, the heat escapes almost completely into space, leaving the surface unimaginably cold. This endless rhythm of intense heat followed by profound cold has repeated itself for billions of years. If you were to stand somewhere near the moon's equator, you would experience one of the most dramatic temperature changes anywhere in the solar system. Yet strangely, scientists eventually realised there were places where this familiar cycle never happened at all. Those places lie near the lunar poles. Unlike Earth, whose axis leans noticeably as it journeys around the Sun, the moon tilts by only a very small amount. It is such a subtle inclination that sunlight always approaches the poles from almost the same low angle. Tall crater walls cast extraordinarily long shadows, and some of those shadows never move away. Imagine placing a bowl outside during a winter afternoon, when the sun hangs low above the horizon. If the bowl is deep enough, its bottom may never receive direct sunlight. Now imagine that bowl remaining in exactly the same position, not for an afternoon, but for millions of years. That is remarkably close to what happens inside certain craters near the moon's north and south poles. Scientists call these places permanently shadowed regions. The name sounds technical, but the idea is beautifully simple. They are places where sunrise never comes. Some of these hidden landscapes have remained untouched by direct sunlight for periods so long that they stretch beyond ordinary imagination. While mountains, oceans, and forests on Earth constantly change through weather, flowing water, and living organisms, these silent lunar craters have rested in darkness through the rise and fall of entire species on our own planet. Inside them, temperatures become astonishingly low. Some measurements suggest that a few of these shadowed locations are colder than the average temperatures found on Pluto, a distant world orbiting far beyond Neptune. In fact, certain small pockets within these craters may rank among the coldest, naturally occurring places anywhere in our solar system. It feels almost poetic. The moon, which appears bright and glowing in our night sky, quietly hides some of the darkest and coldest places known to science, and it is precisely because they are so cold that they became the focus of one of the greatest scientific searches of the modern era. Water behaves differently depending on its surroundings. On Earth, a puddle left under the summer sun slowly disappears into the air. A layer of morning dew vanishes shortly after sunrise. Snow melts into streams, rivers, and lakes before eventually returning to the sky as invisible vapor. Our planet is full of movement. The moon is different. There is almost no atmosphere waiting to receive evaporating water. If exposed directly to sunlight, water molecules gain enough energy to escape into space. There is very little to stop them, unless they arrive somewhere where the sun never shines. Scientists began describing these permanently shadowed craters as natural cold traps. The phrase sounds wonderfully mysterious, yet the idea is surprisingly familiar. Most of us have reached into the back of a freezer and discovered something forgotten long ago. Hidden behind newer food, protected from warmth each time the door briefly opens, it remains frozen year after year. A lunar cold trap works in much the same way. Instead of protecting frozen food, it protects tiny wandering water molecules. Whenever a molecule of water somehow drifts into one of these frozen depressions, the intense cold removes almost all of its energy. Rather than continuing its journey across the moon, it freezes in place. One molecule becomes several. Several become thousands. Over immense stretches of time, those countless tiny arrivals may slowly build deposits of ice hidden beneath perpetual darkness. For many years, scientists imagined these cold traps only inside the largest craters visible from orbit. It seemed logical that only enormous basins could remain permanently frozen. Then an even more intriguing possibility emerged. Perhaps the moon did not possess merely hundreds of cold traps. Perhaps it possessed billions. Researchers began studying the lunar landscape at much finer detail than ever before. They discovered that countless tiny hollows, cracks, shallow depressions, and small craterlets might also remain permanently shaded. These miniature shelters became known as microcold traps. Unlike the giant craters that stretch for kilometers across the lunar surface, some microcold traps may be no larger than a dining table. Others might fit comfortably inside an ordinary living room. Many are so small that they would barely attract your attention if you walked past them, yet together they may cover an enormous total area. It is a little like discovering that instead of storing all your valuables inside one enormous safe, someone has quietly hidden them inside millions of tiny lockboxes scattered across an entire city. Finding each individual box becomes much harder, but together they may hold an extraordinary treasure. This new idea transformed the search for lunar water once again. Scientists were no longer searching only for vast frozen lakes buried inside giant craters. Instead, they began imagining a landscape filled with countless invisible freezers, each quietly preserving tiny amounts of ice across the polar regions. Suddenly, the moon seemed less like a barren desert, and more like an intricate puzzle, with its most valuable pieces hidden in plain sight. Of course, another mystery immediately followed. Even if these natural freezers existed, how had they been filled in the first place? Water could not simply appear out of nothing. Somewhere in the moon's long history, something must have carried it there, created it there, or perhaps continued renewing it even today. As scientists prepared new missions and developed more sensitive instruments, the search gradually shifted from asking where water might survive to something even more fascinating. Who, or perhaps what, keeps delivering water to a world that seems determined to lose it? That gentle question would lead researchers toward invisible streams flowing from the sun, tiny visitors arriving from deep space, and discoveries that would reveal the moon to be far more active than anyone had imagined. Once scientists had identified places cold enough to preserve water for billions of years, the next challenge seemed wonderfully straightforward. All they had to do was look. At least that was the hope. Instead, the moon responded with another quiet mystery. Again and again, spacecraft arrived carrying increasingly sophisticated instruments. Each mission improved upon the last, peering into shadows, measuring invisible wavelengths of light, and searching for the faint chemical fingerprints that water leaves behind. Every new generation of explorers expected the puzzle to become simpler. Instead, it became stranger. The first major breakthrough came during the 1990s, when NASA launched a spacecraft called Clementine. Its primary purpose was not to search for water alone, but as it carefully mapped the lunar surface, it confirmed something that changed the direction of lunar science forever. Near the moon's south pole were enormous craters whose floors had remained hidden from sunlight for unimaginably long periods of time. Scientists suddenly had real places to investigate. It was rather like searching for a missing treasure map and unexpectedly discovering the location where the treasure might actually be buried. Naturally, curiosity grew. Soon afterward, another spacecraft called Lunar Prospector began studying the poles from orbit. Instead of taking ordinary photographs, it searched for hydrogen, one of the essential building blocks of water. Its instruments detected unusually large amounts near both lunar poles. The discovery was exciting, but excitement quickly gave way to caution. Hydrogen alone does not necessarily mean water. It could belong to water molecules. Or it could belong to a closely related substance called hydroxyl, where oxygen is joined with only a single hydrogen atom instead of forming a complete water molecule. The spacecraft had found a clue, not a conclusion. Scientists were left standing at another crossroads. The evidence suggested something important was hiding there. They simply could not yet say exactly what it was. To settle the question, NASA made a bold decision. When Lunar Prospector had completed its mission, controllers deliberately guided it into a crash near the moon's south pole. The hope was beautifully simple. If the impact threw frozen material into sunlight, telescopes on Earth might finally detect unmistakable signs of water. The spacecraft struck exactly as planned. Scientists watched carefully. Nothing conclusive appeared. The moon kept its secret. Several years later, Japan launched another lunar explorer called Kaguya, also known as Selene. Its cameras and scientific instruments mapped the moon with remarkable detail, offering humanity one of its clearest views yet of our nearest celestial neighbour. Yet when its mission ended, it too became part of the investigation. Like Lunar Prospector before it, Kaguya was intentionally guided into the lunar surface, allowing researchers one more opportunity to study the material thrown upward by the impact. Again, the answer remained frustratingly elusive. If water was there, it refused to reveal itself so easily. By now, the search had begun to resemble a patient detective story, rather than a straightforward scientific experiment. Each mission uncovered another clue. Each clue led to another question. Then, in 2008, the story quietly changed direction. India launched its first mission to the moon. Rather than relying only on distant observations, Chandrayaan-1 carried instruments capable of studying the lunar environment in a new way. As one part of the spacecraft descended toward the surface near the South Pole, it measured the extremely thin layer of particles surrounding the moon. During that descent, scientists finally received the evidence they had been waiting for. Water. Not merely a hint, not simply hydrogen, but convincing evidence that water really did exist on the moon. For many researchers, it was one of those unforgettable scientific moments when decades of careful work suddenly came together. The answer had been there all along, or at least part of the answer. Because only a few months later, another instrument aboard Chandrayaan-1 added an even greater surprise. As it studied sunlight reflected from the lunar surface, it found signs of water not only near the poles, but across much wider regions of the moon. The discovery gently challenged nearly everything scientists thought they understood. If water existed over much of the lunar surface, then perhaps the moon was not simply hiding isolated pockets of ice. Perhaps the entire world was participating in a far more subtle process. NASA, eager to confirm these remarkable discoveries, soon launched another carefully designed mission known as the Lunar Crater Observation and Sensing Satellite, or LCROSS. Its plan was wonderfully inventive. Instead of landing softly, the mission deliberately released part of its rocket to crash into a permanently shadowed crater. Moments later, the spacecraft itself flew directly through the rising cloud of dust and vapor, sampling its contents before completing its own mission with a final impact. Unlike earlier attempts that relied on telescopes watching from hundreds of thousands of kilometers away, LCROSS travelled straight through the plume itself. The results were extraordinary. Scientists detected clear evidence of water. They also found other frozen compounds, including ammonia and methane, along with additional hydrogen that could one day become valuable resources for future explorers. The long debate was finally over. The moon was not dry. But almost immediately a new mystery appeared. How much water was actually there? Where exactly was it hiding? And why did it seem so difficult to observe directly? Meanwhile, another spacecraft quietly continued circling above. The Lunar Reconnaissance Orbiter spent year after year mapping the moon in extraordinary detail. As its observations accumulated, researchers noticed something even more surprising than hidden ice at the poles. Tiny amounts of water appeared to exist almost everywhere. The quantities were incredibly small, nothing like lakes, rivers, or glaciers. If gathered together, they would scarcely resemble the water we know on Earth. Yet their behaviour fascinated scientists. As the long lunar morning gradually warmed the surface, the signals associated with water became weaker. Later, as evening slowly returned and temperatures fell again, those signals appeared to strengthen. It almost seemed as though the moon itself was breathing, not with air, of course, but with an almost invisible rhythm, where tiny water molecules wandered gently across the surface, responding to the slow rise and fall of temperature throughout the lunar day. Some researchers began describing this as a kind of lunar water cycle. It is nothing like Earth's familiar cycle of clouds, rainfall, rivers and oceans. Instead, imagine a few delicate snowflakes drifting quietly across an enormous frozen landscape, disappearing into sunlight before settling again when darkness returns. The movement is subtle, almost imperceptible. Yet over immense spans of time, even these tiny journeys may shape the moon's hidden reservoirs of water. Then another remarkable discovery added yet another twist. Using an airborne observatory called SOFIA, scientists detected water within one of the moon's sunlit craters. Until then, many researchers had assumed that meaningful amounts of water could survive only inside permanently shadowed regions. Now it appeared that at least small quantities also existed where sunlight reached the surface. The mystery grew deeper once again. The more carefully humanity observed the moon, the less ordinary it became. Instead of a lifeless sphere of dry rock, our nearest neighbour began revealing itself as a world where invisible water quietly appeared, disappeared, wandered across the landscape and settled into places colder than almost anywhere else in the solar system. Somewhere within that gentle hidden dance lay the answer to a question that scientists were only beginning to ask. If water could move across the moon like this, where had it come from in the first place? By now, scientists had accepted something that once seemed almost impossible. The moon really does contain water. Not oceans, not flowing rivers, not frozen landscapes stretching across the horizon. Instead, tiny amounts appeared in places that seemed almost impossible to predict. Some hid inside permanently shadowed craters, some appeared across sunlit regions, some seemed to wander gently across the surface as temperatures changed throughout the lunar day. Finding water had solved one mystery, but almost immediately it created another. Where had all of it come from? If you were standing on the moon billions of years ago, you would have seen a world that looked very different from the peaceful companion we admire today. Instead of quiet nights beneath Earth's sky, the young moon endured an age of relentless bombardment. Countless asteroids and comets crossed the inner solar system, crashing into the surfaces of the growing planets with unimaginable force. Many scientists believe this violent era may have delivered the moon's very first supply of water. Comets are sometimes described as dirty snowballs, although that phrase hardly captures their complexity. They are ancient travellers carrying mixtures of frozen water, dust, carbon-rich materials, and other compounds that have remained preserved since the earliest days of the solar system. Every impact released enormous amounts of energy. Rock melted, dust exploded outward, fragments scattered across the landscape. Some of the water carried by those ancient visitors may have survived the chaos, gradually finding its way into the permanently shadowed craters that we explored earlier. If this idea is correct, then some of the ice resting quietly near the lunar poles today may be older than nearly every mountain, forest, or ocean on Earth. It could be a frozen memory of the solar system's earliest chapter. Yet this explanation raises another gentle question. If the moon received most of its water billions of years ago, why do scientists continue detecting signs that water is still changing today? Something else may still be happening. To understand the next possibility, we need to turn our attention away from the moon entirely and instead look toward the sun. When we picture sunlight, we usually imagine warmth and brightness. But the sun is doing far more than simply shining. Every second it releases a constant stream of incredibly tiny particles flowing outward in every direction. This invisible flow travels across the solar system continuously, passing planets, moons, asteroids, and spacecraft alike. Scientists call this flow the solar wind. Although the name sounds dramatic, it is helpful to imagine it not as a powerful hurricane, but as an extraordinarily gentle breeze that never stops blowing. You would never feel it against your skin on Earth because our atmosphere and magnetic field protect us so effectively. The moon, however, has almost no atmosphere and no global magnetic shield. Its surface stands directly exposed. Among the countless particles carried by this invisible breeze are tiny hydrogen atoms. When they strike the lunar soil, something rather remarkable can happen. Much of the moon's surface is made from minerals containing oxygen locked inside rock. If incoming hydrogen meets that oxygen under the right conditions, simple chemical reactions may occur. Tiny new compounds begin to form. Some become hydroxyl, others may eventually become water molecules. Rather than imagining complicated chemistry, it may be easier to picture a craftsman slowly adding missing pieces to an unfinished puzzle. One tiny piece arrives, another follows. Over immense periods of time, simple ingredients quietly assemble into something new. The process is incredibly slow, almost unimaginably gentle. Yet the solar system has had billions of years to work with. If this idea is correct, then the moon is not merely preserving ancient water, it may still be helping create small amounts of it today. Another possibility arrives from a very different direction. Every day, the moon is struck by countless micrometeorites. Most are no larger than grains of sand. Some are smaller than grains of dust. Unlike the dramatic asteroid impacts often shown in films, these tiny visitors arrive almost continuously, silently peppering the lunar surface day after day. At first glance, they seem too small to matter, but imagine rain falling onto a stone path. One drop changes almost nothing. A billion drops slowly reshape the surface. Micrometeorites may work in much the same way. Some carry tiny amounts of water themselves, others generate intense bursts of heat when they strike, briefly melting microscopic portions of lunar soil before everything cools again. Within those tiny flashes of molten material, something extraordinary may happen. As the melted droplets rapidly cool, they solidify into tiny glass beads. For many years, scientists assumed these beads were little more than ordinary fragments created during impacts. Then researchers made an exciting discovery. Some of these microscopic glass beads appear capable of storing water. Even more intriguingly, they may act almost like miniature rechargeable batteries. During the long lunar daytime, hydrogen arriving with the solar wind can interact with the beads. Later, when conditions change, some of that water may be released again. Imagine millions upon millions of tiny glass pearls scattered across the moon's dusty surface, each one quietly collecting, storing and releasing tiny amounts of water over countless cycles. No individual bead contains very much, yet together they may represent another important piece of the lunar puzzle. Scientists have also suggested that some water never reaches the surface at all. Instead, it may hide between grains of lunar dust. The moon's soil, known as regolith, is far more complex than it first appears. Rather than behaving like ordinary sand on a beach, it resembles an intricate mixture of shattered rock, mineral fragments, microscopic glass, and fine powder produced by billions of years of impacts. Within those tiny spaces between individual grains, water molecules may find brief shelter from the harsh sunlight above. It is a little like morning dew lingering beneath thick grass long after the surrounding ground has already dried. The protection is subtle, but sometimes subtle protection is enough. Perhaps the most fascinating realization is that none of these ideas necessarily excludes the others. Ancient comets may have delivered enormous quantities of water long ago. The solar wind may still contribute tiny amounts every single day. Micrometeorites may constantly reshape the surface while creating new places for water to hide. Glass beads may quietly store and release moisture. Frozen craters may preserve it. Dust grains may shelter it. Instead of one grand explanation, the moon may be telling several stories at once. Nature often prefers cooperation over simplicity. As more evidence accumulated, scientists gradually stopped asking which single theory was correct. Instead, they began asking how all these processes might work together over billions of years. It was a quieter way of thinking, a more patient way, and perhaps a more beautiful one as well. Because the moon no longer appeared to be a silent world that had simply received water long ago. It began to resemble a place where invisible processes were still unfolding every day, far too slowly for human eyes to notice, yet steadily shaping the future of one of humanity's greatest adventures. If that invisible work has truly been continuing for billions of years, then another question naturally follows. Even if we know where some of the water comes from, how could we ever hope to collect it? If someone were to hear that scientists had discovered water on the moon, the next thought might seem almost automatic. Wonderful. Now all we have to do is collect it. It sounds simple enough. After all, here on Earth, if you discover a frozen lake, you know where the water is. If you need more, you drill through the ice or wait for it to melt. We have spent thousands of years learning how to gather water from rivers, glaciers, underground reservoirs, and even the air itself. Surely the moon would simply require a more sophisticated version of the same idea. But the moon has a remarkable habit of making simple ideas unexpectedly difficult. Finding water is one challenge. Living where that water exists is another entirely. The place is believed to contain the richest stores of lunar ice, are also among the most hostile environments ever encountered by human explorers. Imagine standing at the edge of a vast crater whose floor has never seen sunlight. There is no sunrise waiting just beyond the horizon, no warm afternoon, no golden evening, only darkness. Not the comforting darkness of a quiet bedroom after sunset, but a darkness so complete that it has lasted for millions, perhaps even billions of years. Even the stars above provide little comfort. Without sunlight reaching the crater floor, temperatures remain unimaginably low. Some locations become colder than almost anywhere else naturally found in our solar system. Machines that work perfectly on Earth may become brittle, metals shrink, lubricants freeze, batteries lose efficiency. Electronics must struggle simply to stay warm enough to function. Ironically, this safest place for water may be one of the least welcoming places for people. Even reaching these craters presents enormous challenges. The sun never climbs high above the horizon near the lunar poles. Long shadows stretch across the landscape, hiding steep slopes, scattered boulders, and deep depressions. A rover driving across this terrain cannot simply rely on ordinary cameras. Obstacles emerge slowly from the darkness, often only after the vehicle has already approached them. It is rather like walking through a familiar room in the middle of the night using only a small flashlight. Every step demands patience. Every shadow deserves respect, and yet the darkness itself is only the beginning. Another obstacle lies quietly beneath every footprint: lunar dust. Calling it dust almost sounds harmless. It brings to mind the fine powder resting on an old bookshelf, or the soft flour scattered across a kitchen counter. Lunar dust is nothing like either of those. Imagine taking powdered glass, crushing it into particles finer than flour, then removing every trace of wind and rain that might smooth their edges over time. Each tiny grain remains sharp, angular, jagged. Billions of years of constant meteorite impacts have shattered the lunar surface into microscopic fragments without the gentle weathering processes that soften rocks on Earth. During the Apollo missions, astronauts quickly discovered that this dust clung stubbornly to everything. It covered boots, it coated gloves, it worked its way into joints, seals, cameras, scientific instruments, and mechanical equipment. No matter how carefully they tried to brush it away, it always seemed determined to stay. One astronaut compared its persistence to trying to remove dry charcoal powder after it had already worked itself into clothing. The comparison is wonderfully ordinary, yet it captures the problem surprisingly well. The dust simply refuses to let go. Part of the reason lies in electricity. Here on Earth, you may have experienced the tiny surprise of walking across a carpet on a dry day before touching a metal doorknob. A small spark jumps between your finger and the metal. It lasts only an instant, yet it reminds you that invisible electrical charges can quietly build up around us. Something similar happens on the Moon. The constant stream of charged particles flowing outward from the Sun interacts directly with the lunar surface. Without a thick atmosphere to soften these interactions, electrical charges can gradually build across the dusty landscape. As a result, many dust particles become electrically attracted to nearby surfaces. Instead of falling quietly back to the ground, they cling to spacesuits, scientific equipment, solar panels, and vehicle windows almost as though they were alive. Scientists often describe this as electrostatic dust. For future astronauts, it may feel more like trying to work inside a room where glitter constantly floats through the air, except this glitter is abrasive enough to slowly wear away machinery designed to keep people alive. The dust presents another concern as well. Because the particles are so incredibly small, they can easily become airborne for short periods after landings or vehicle movements. If brought inside a habitat, they may irritate both equipment and people. The Apollo astronauts reported sore throats, watery eyes, and coughing after returning inside with lunar dust covering their suits. Future settlements hoping to remain on the moon for months or even years cannot simply accept those conditions. They must find ways to keep the dust outside. Fortunately, engineers are already imagining remarkably creative solutions. Some research teams are developing electrically charged surfaces capable of gently pushing dust away before it accumulates. Rather than scrubbing equipment by hand, these surfaces create carefully controlled electrical waves that encourage the particles to slide away, almost like tiny leaves carried across a smooth pavement by a light breeze. Other researchers are exploring methods that use extremely cold liquids to trap dust before it can spread through a habitat. Meanwhile, robotic systems are becoming increasingly sophisticated. Instead of asking astronauts to spend long hours working in dangerous environments, engineers envision machines carrying out much of the hardest labour. Some robots may excavate frozen soil, others may transport material back to processing stations. Still others may be controlled remotely by astronauts working safely inside warm, pressurised habitats, guiding heavy machinery almost as comfortably as someone operating advanced construction equipment from a protected control room. In many ways, the first permanent lunar settlements may resemble quiet partnerships between people and machines, rather than heroic adventures carried out by humans alone. Yet perhaps the greatest challenge of all is not technological, it is practical. Even if scientists know that water exists somewhere inside a permanently shadowed crater, that does not mean they know exactly where to dig. Unlike a frozen lake on Earth, lunar ice may not form large continuous sheets. It may be mixed with dust, hidden between rocks, trapped inside microscopic glass beads, buried beneath several centimetres, or perhaps even metres of regolith. Imagine searching for tiny crystals of frost hidden somewhere beneath an enormous desert, knowing only that they probably exist. That is remarkably close to the challenge facing today's lunar scientists. Finding water on the moon is not simply about reaching the correct crater. It is about understanding an entire hidden landscape that refuses to reveal itself all at once. And perhaps that is exactly why each new mission continues to uncover fresh surprises. Because the moon does not surrender its secrets quickly, it reveals them patiently, one careful discovery at a time, inviting us to slow down, observe more closely, and remember that exploration is rarely a straight path. Sometimes the greatest discoveries belong not to those who rush forward, but to those willing to keep searching long after the first answers have appeared. For thousands of years, civilizations have risen beside water. The earliest cities grew along rivers, farms flourished where fresh water could nourish crops. Great ports became centres of trade because ships could carry both people and resources across vast distances. Long before humanity understood chemistry, engineering or astronomy, we had already learned one simple lesson. Where there is reliable water, life becomes possible. Perhaps that is why the search for water on the moon has captured so much attention. It is not because water itself is rare in the universe. We now know that water exists on icy moons, frozen comets, distant asteroids, and even hidden beneath the surfaces of planets. The moon is different for one very important reason. It is close enough that we can realistically imagine living there. And if people are ever to stay on the moon for months, years, or even generations, water will quietly become the foundation beneath almost every part of daily life. The most obvious use is, of course, drinking. A human being can survive for weeks without food, but only a few days without water. Every astronaut living on a future lunar base will depend upon a reliable supply simply to remain healthy. But drinking is only the beginning. Water is also essential for preparing food, maintaining hygiene, cleaning equipment, and supporting medical care. Every ordinary activity that we rarely think about on Earth suddenly becomes precious when every single drop must either be transported across space or carefully recycled. Fortunately, astronauts have already become remarkably efficient at recycling water aboard spacecraft. On the International Space Station, water is continuously purified and reused through advanced life support systems. Moisture from the air, water used for washing, and even water recovered from human waste are all carefully cleaned before returning to the station supply. It may sound unusual at first, but it reflects one of the oldest lessons in nature. Nothing is wasted. A future lunar settlement will almost certainly work in much the same way. Instead of constantly waiting for supply rockets from Earth, every drop will be treated as part of a carefully balanced cycle. You might imagine it as a quiet garden fountain. The same water keeps circulating, flowing through different paths before gently returning once again. The goal is not simply to use water, the goal is to keep it moving. Water also makes another extraordinary contribution that is much less obvious. It can help astronauts breathe. Of course, no one breathes liquid, water directly. Instead, scientists can separate water into two invisible gases. One becomes oxygen, the very gas that fills our lungs with every breath we take. The other becomes hydrogen, an element that may prove equally valuable for entirely different reasons. Together, these two gases have powered many of humanity's rockets for decades. In other words, water is not simply something astronauts drink. It can also become the fuel that carries spacecraft deeper into space. That idea is quietly revolutionary. Imagine setting out on a long road trip. Normally, you would leave home with a full tank of fuel because there might be no petrol stations for hundreds of kilometers. Now imagine that halfway through your journey you discover a fully equipped service station waiting beside the road. Suddenly your entire journey changes. You no longer need to carry all your fuel from the beginning. The moon could become something very similar. Not a roadside petrol station, of course, but the first refueling stop between Earth and the rest of the solar system. Many engineers already describe this vision as a lunar fuel depot. The idea is surprisingly simple. Instead of launching enormous quantities of rocket fuel from Earth's powerful gravity, spacecraft could travel to the moon, replenish their supplies using fuel produced from local water, and then continue onward toward Mars, nearby asteroids, or even more distant destinations. This matters because escaping Earth's gravity is incredibly expensive. Every kilogram launched from Earth requires fuel, but carrying more fuel also adds more weight. That additional weight demands even more fuel. It becomes a cycle that grows heavier with every step. The moon changes that equation. Its gravity is only about 1/6 as strong as Earth's. Launching a spacecraft from the lunar surface requires far less energy than launching the same spacecraft from our own planet. Rather than climbing out of a deep valley, it is more like walking up a gentle hill. That single difference could reshape the economics of future space travel. Water offers still another remarkable advantage. It provides protection. Beyond Earth's atmosphere, astronauts are exposed to powerful cosmic radiation and energetic particles arriving from the sun. Our planet's magnetic field quietly shields us from much of this invisible bombardment every day. The moon offers no such protection. Yet water happens to be surprisingly good at absorbing certain forms of radiation. Instead of surrounding habitats entirely with thick metal walls, future lunar bases may store tanks of water around sleeping quarters or living spaces, creating an additional layer of protection between astronauts and the harsh environment outside. It is a beautiful example of one resource performing several jobs at once. Water becomes something to drink, something to breathe, something to launch rockets, and something that quietly helps protect human life. It may even help future explorers grow food. Plants need more than sunlight and soil. They require water to move nutrients through their leaves, build new cells, and produce the oxygen that supports animal life. Scientists envision future lunar greenhouses where vegetables, grains, and perhaps even fruit could be grown inside carefully controlled environments. Picture a greenhouse glowing softly against the endless darkness of the lunar landscape. Outside, the surface remains silent, grey and frozen. Inside, green leaves gently reach toward carefully arranged lights, nourished by water that may have rested beneath the moon's surface for billions of years before becoming part of humanity's first extraterrestrial garden. That image feels almost dreamlike, yet engineers are already designing systems intended to make such places possible. Over time, all these separate uses begin connecting together. Water supports people. People maintain equipment. Equipment extracts more water. Water grows food. Water produces oxygen. Water creates fuel. Fuel allows new missions. New missions expand the settlement. What first appeared to be a single resource gradually reveals itself as the foundation of an entire ecosystem. Perhaps this is why some scientists have quietly begun referring to water as the oil of space, not because the two substances resemble one another, but because each has the power to transform economies, technologies, and patterns of exploration. Centuries ago, rivers connected civilizations. Today, oceans connect continents. One day, water on the moon may connect worlds, and if that future begins to unfold, another fascinating question naturally follows. Water alone will never build an entire civilization. What other treasures might already be waiting beneath the moon's quiet grey surface, ready to support humanity's next great chapter among the stars? For much of the 20th century, reaching the moon was seen as the finish line. Landing there represented one of humanity's greatest technological achievements. Flags were planted, scientific instruments deployed, rocks collected, and history was made. Once those remarkable missions ended, many people imagined that the great lunar adventure had reached its natural conclusion. But history has a curious way of changing its mind. Today, the moon is no longer viewed as the end of a journey. Instead, it is increasingly being seen as the beginning of another. As scientists gradually uncovered stronger evidence that water exists on the moon, governments and space agencies around the world began looking at our nearest celestial neighbour through entirely new eyes. The moon was no longer simply a destination for short scientific visits. It was becoming a place where people might one day stay. If you were to look at maps produced by different space agencies today, you would notice something interesting. Again and again, attention returns to the same general region, the lunar South Pole. At first, this might seem like a coincidence, but the reasons are surprisingly practical. The South Polar region appears to offer one of the best combinations of resources and environmental conditions anywhere on the moon. Nearby permanently shadowed craters may contain valuable stores of frozen water. At the same time, certain mountain ridges and elevated areas receive sunlight for much longer periods than most other locations, providing opportunities to generate electricity using solar panels. In other words, one part of the landscape may provide the water, another part may provide the energy. Together, they begin to resemble the ingredients needed for a permanent settlement. That realization has quietly transformed the moon into one of the most important destinations in modern space exploration. The United States, through NASA's Artemis program, hopes to establish a lasting human presence near the lunar South Pole. Rather than repeating the brief visits of the Apollo era, the long-term vision is to create a sustainable system of exploration where astronauts return again and again, gradually building the experience needed for even more ambitious journeys. Meanwhile, China has outlined an equally ambitious series of lunar missions, working alongside international partners to develop what is known as the International Lunar Research Station. Their long-term goal is not simply to land on the moon, but to establish robotic facilities that may eventually support human explorers as well. India continues expanding its lunar program, following the remarkable achievements of Chandrayaan missions, each one adding new pieces to the puzzle of the moon's geology and hidden water. Japan contributes advanced engineering and robotic technologies that could prove invaluable for future exploration. South Korea has already demonstrated its growing capabilities through the Danuri lunar orbiter, whose remarkably sensitive camera has allowed scientists to peer more deeply into permanently shadowed craters than ever before. The European Space Agency continues collaborating on technologies, scientific instruments, and future exploration concepts designed to support long-term lunar operations. Rather than a single nation racing alone, the moon is gradually becoming a place where many countries pursue different pieces of the same enormous challenge. Of course, cooperation and competition often exist side by side. Throughout history, major periods of exploration have usually combined both. The age of sail connected continents, the age of flight connected nations. Perhaps the coming decades will become known as the age of lunar exploration. Yet building a settlement on another world requires much more than simply landing astronauts. Imagine trying to establish a village in one of Earth's most remote deserts, while carrying every drop of water, every piece of food, every brick, every window, every tool, and every litre of fuel from another continent. Eventually, the transportation alone becomes overwhelming. Future lunar explorers hope to avoid exactly that problem. Instead of bringing everything from Earth forever, they want to learn how to use the resources already waiting on the moon itself. Scientists call this idea in situ resource utilization, but the concept is far simpler than the name might suggest. Imagine arriving at a campsite beside a forest. Rather than bringing every piece of firewood from home, you gather fallen branches already lying nearby. Rather than carrying stones for a campfire, you use rocks already resting on the ground. The moon asks us to think in much the same way. If water already exists there, perhaps it should become the settlement's water. If oxygen can be produced there, perhaps it should become the settlement's air. If local materials can be turned into building supplies, perhaps future habitats should be constructed using lunar soil rather than materials launched from Earth. Every kilogram that does not need to cross nearly 400,000 kilometers of space makes future exploration a little easier. Water, however, is only one of several valuable resources attracting scientific attention. The moon's surface also contains large quantities of metals such as iron, aluminium, titanium, silicon, calcium, and magnesium. None of these elements are especially rare on Earth, yet transporting them through space is enormously expensive. Being able to produce building materials directly on the moon would fundamentally change how future settlements are designed. Researchers have even developed ideas for transforming lunar soil into a material sometimes called lunar concrete. Instead of shipping bricks across space, explorers may eventually build roads, landing pads, storage facilities, and protective walls using the dusty ground already beneath their feet. The moon, in a sense, could slowly become its own construction site. Another resource has captured the imagination of scientists for decades: helium-3. It sounds almost like something from science fiction, yet it is a genuine form of helium that exists only in extremely small quantities on Earth. Our planet's magnetic field quietly shields us from much of the solar wind, deflecting many incoming particles before they ever reach the ground. The moon has no such global protection. For billions of years, particles carried by the solar wind have gently settled into the lunar soil. Among them is helium-3. Although present only in tiny concentrations, it has attracted considerable interest, because future fusion technologies may one day use it as a potential fuel source. Whether that vision eventually becomes practical remains uncertain, yet the possibility alone has encouraged researchers to study the moon's resources with increasing attention. The moon also contains deposits of materials known as rare earth elements. Curiously, the name is slightly misleading. Many of these elements are not truly rare. Instead, they are simply difficult to gather economically because they are widely scattered across Earth's crust. These materials are important for modern electronics, batteries, renewable energy technologies, and countless everyday devices that quietly shape our lives. Understanding where similar materials exist on the moon may become increasingly important as humanity expands its activities beyond Earth. Taken together, these discoveries paint a fascinating picture. The moon is not simply a world of rocks and dust. It is a place containing water, metals, building materials, and perhaps even future energy resources. Suddenly, the search for water becomes something much larger. It becomes part of a broader question. If humanity can learn to live using the resources of another world, then perhaps our first permanent settlement beyond Earth will not survive because of supplies delivered from home, Perhaps it will thrive because it learns to work in harmony with the quiet gifts that have been waiting beneath the moon's surface all along. As humanity's understanding of the moon has grown, something rather remarkable has happened. The questions scientists ask have gradually changed. A century ago, we wondered what the moon was made of. Half a century ago, we wondered whether people could safely walk upon its surface. Today, another question quietly takes centre stage. Could the moon become humanity's first permanent home beyond Earth? Not a replacement for our own planet, not a second Earth, but something entirely new, a place where explorers pause before continuing farther into the solar system. Throughout history, every great journey has depended on places where travellers could rest, repair, and prepare for what lay ahead. Ancient caravans crossed deserts from one oasis to another. Sailing ships relied upon sheltered ports where fresh water, food, and supplies could be gathered before crossing vast oceans. Modern aircraft stop at airports before continuing across continents. Perhaps one day, spacecraft will do something surprisingly similar. The moon may become the first harbour in space. The word harbour usually brings to mind calm water, quiet docks, and ships gently rising and falling with the tide. The moon, of course, has none of these things. There are no oceans, no waves, no sea breeze. Yet in another sense, the comparison feels surprisingly appropriate. A harbour is not defined by water. It is defined by purpose. It is a place where journeys begin again. Imagine a spacecraft leaving Earth on a mission to Mars. Instead of carrying every kilogram of fuel, oxygen, water, spare equipment, and scientific supplies from the very beginning, it could first travel to a lunar base. There, astronauts might replenish their resources, inspect their spacecraft, perform repairs, replace worn equipment, and prepare carefully before beginning the much longer voyage outward. The journey becomes easier because it is divided into smaller steps. Anyone who has climbed a long mountain trail knows the value of resting at a campsite before continuing upward. The moon could become that campsite for humanity's expansion into space. This idea grows even more interesting when we remember something discussed earlier. Water does not simply support life, it also becomes rocket fuel. If future settlements learn how to extract water efficiently from lunar ice, separate it into hydrogen and oxygen, and store those materials safely, then spacecraft departing from the moon may no longer depend entirely upon fuel launched from Earth. The consequences would reach far beyond the moon itself. Missions to Mars could become more practical. Scientific expeditions to nearby asteroids might become more frequent. Robotic explorers travelling toward the outer planets could depart carrying additional scientific instruments instead of enormous quantities of fuel. One resource quietly changes the mathematics of exploration. But transportation is only part of the picture. A permanent lunar settlement would also become a centre for scientific discovery. The moon offers a unique environment unlike anywhere on Earth. Its slow rotation creates long periods of uninterrupted daylight and equally long periods of darkness. It has almost no atmosphere to blur distant starlight. Radio signals from Earth cannot easily reach certain regions on the far side of the moon, making them unusually quiet from an astronomical perspective. Imagine building a giant radio telescope in a place where the constant chatter of human technology grows wonderfully faint. It would be like stepping away from a crowded city into a peaceful mountain valley, where distant whispers suddenly become easier to hear. Some astronomers believe the far side of the moon could become one of the finest places in the solar system to observe the early universe. Other scientists imagine laboratories studying how plants grow under low gravity, how materials behave after years of exposure to space, or how humans adapt to living beyond Earth for extended periods. In that sense, a lunar settlement would be more than a mining outpost. It would become a living laboratory, a classroom, a workshop, a place where each generation prepares the next. Of course, whenever valuable resources are involved, another question naturally appears. Who owns them? The answer is more complicated than many people expect. More than half a century ago, nations came together to establish principles for peaceful exploration beyond Earth. One of the most important agreements became known as the Outer Space Treaty. Its central idea is both simple and profound. No nation may claim ownership of the Moon itself. Unlike islands discovered during earlier centuries on Earth, no country can simply arrive, plant a flag, and declare an entire world its own. That principle has helped keep space exploration remarkably peaceful. Yet the treaty leaves another question far less certain. If no one owns the Moon, who owns the resources extracted from it? Imagine hikers walking through a public forest. No individual owns the forest itself. But if someone gathers fallen branches for a campfire, who owns the wood? The comparison is not perfect, but it hints at the kind of discussions scientists, lawyers, engineers, and governments continue having today. Some believe resources should belong to whoever extracts them. Others argue that space should remain a shared heritage for all humanity. Still, others propose entirely new systems of international cooperation. For now, many of these questions remain unanswered. Perhaps that uncertainty is not surprising. History often shows that laws evolve alongside technology. People rarely write detailed rules for activities that have not yet become possible. Before the invention of airplanes, no one needed international aviation law. Before satellites, no one imagined regulations for objects orbiting Earth. Likewise, humanity is only beginning to think seriously about living and working on another world. As these possibilities move from imagination toward reality, our understanding of responsibility must grow alongside our technology. There is another reason this matters. The Moon is close enough that mistakes made there can still be corrected. Communication with Earth takes only a little over 1 second each way. Supplies, although expensive, can still be delivered. Rescue missions remain extraordinarily difficult, but they are not beyond imagination. Mars will be different. Messages take many minutes to arrive. Resupply missions require years of planning. Astronauts will often need to solve problems entirely on their own. In many ways, the Moon offers humanity something priceless: practice. A place to learn how to live wisely beyond Earth before attempting far greater journeys. Perhaps that is the Moon's greatest gift. Not simply water, not metals, not fuel, but experience. A quiet world close enough to teach us lessons that may one day carry us safely across the rest of the solar system. And as every lesson brings new understanding, one final mystery continues waiting patiently beneath the lunar surface. We know the water exists, we know why it matters. Yet after decades of searching, one surprisingly simple question still refuses to disappear. Where, exactly, is it hiding? For a long time, scientists imagined that solving the mystery of lunar water would happen in a familiar way. A spacecraft would arrive. Its instruments would scan the surface. A brilliant photograph would reveal glittering fields of ice hidden inside one of the Moon's permanently shadowed craters. The mystery would be over. Reality, as it often does, proved much more subtle. Instead of finding great frozen lakes waiting quietly in the darkness, every new mission seemed to deepen the mystery a little further. Perhaps the clearest example arrived with a spacecraft that very few people outside the scientific community had heard about. In late 2022, South Korea successfully placed its first lunar orbiter into orbit around the Moon. Its name was Danuri, a word that can be understood as enjoying the Moon. Although it represented a tremendous achievement for South Korea's growing space program, Danuri also carried something built with assistance from NASA. An extraordinary camera called ShadowCam. At first glance, ShadowCam looked rather ordinary. Its real strength was hidden inside its extraordinary sensitivity. Compared with previous lunar cameras, it could detect extremely faint light reflected from nearby mountains and crater walls, allowing scientists to see deep into places that remained almost completely invisible for decades. For the first time, humanity could peer into many permanently shadowed craters with remarkable clarity. Researchers were understandably excited. If water ice had accumulated over billions of years, surely these remarkable new images would finally reveal obvious frozen deposits. Instead, they revealed another question. The craters were certainly there. Their steep walls, rugged slopes, scattered boulders, and ancient landslides became visible in astonishing detail. Yet the bright, unmistakable signatures of large exposed ice deposits remained strangely absent. It was rather like opening an old treasure chest after following a map for many years, only to discover that the chest itself was real, but the treasure was nowhere to be seen. The mystery had not disappeared. It had simply become more interesting. Not long afterward, another remarkable mission added its own chapter to the story. India's Chandrayaan 3 mission successfully landed near the Moon's south polar region, becoming one of the most significant achievements in the history of lunar exploration. Its small rover carefully examined the surrounding soil. Its instruments identified elements such as aluminium, calcium, iron, titanium, sulfur, oxygen, and several others that help scientists understand how the Moon formed and evolved over billions of years. These discoveries alone represented an extraordinary scientific success. Yet many researchers were quietly waiting for something else: hydrogen. Because where hydrogen appears in the right environment, water may not be far away. Surprisingly, the nearby surface showed little evidence of easily accessible water. Once again, scientists found themselves asking the same gentle question. If spacecraft orbiting above the Moon repeatedly detect signs of water, why do landers standing directly on the surface struggle to find it? The answer may have been hiding beneath the astronauts' feet all along. One of Chandrayaan 3's most fascinating experiments did not search directly for water. Instead, it measured temperature. That might sound almost disappointingly simple. After all, measuring temperature seems like one of the oldest scientific tasks imaginable, yet the results were quietly astonishing. Near the surface, sunlight had warmed the ground dramatically. Only a few centimetres lower, however, the temperature had fallen with surprising speed. The lunar soil turned out to be an excellent insulator. Heat did not travel downward very easily. Imagine walking barefoot across a sandy beach on a hot summer afternoon. The top layer feels almost too warm to touch. Yet if you gently push your fingers beneath the surface, the sand only a short distance below often feels pleasantly cool. The Moon behaves in a surprisingly similar way, although under far more extreme conditions. This simple observation may completely reshape the search for lunar water. Perhaps scientists have been looking in the wrong place. Instead of expecting large sheets of ice resting openly on the surface, perhaps much of the Moon's water lies safely hidden beneath a protective blanket of dust and broken rock. Only a few centimetres deeper, perhaps a little farther, perhaps much farther still. That possibility explains many puzzles at once. Orbiting spacecraft detect the chemical fingerprints of water. Landers see very little exposed ice. Both observations may be correct. The water may simply be hiding underground. It is an elegant idea. And like many elegant scientific ideas, it raises even more questions than it answers. How deep are these hidden deposits? Are they scattered evenly across the polar regions, or concentrated in only a handful of locations? How pure is the ice? Can it be mined efficiently? Would extracting it disturb the delicate balance that has preserved it for billions of years? No one knows for certain. Another reminder of how difficult this search can be came from a mission that never had the opportunity to begin. NASA had spent years developing a rover called Viper, short for the Volatiles Investigating Polar Exploration Rover. Unlike previous missions, Viper was designed specifically to roam across the lunar South Pole, drilling beneath the surface and searching directly for hidden ice. It was in many ways exactly the kind of explorer scientists had hoped for. Yet after years of development, budget pressures and schedule delays led to the mission's cancellation. For many researchers, it was a deeply disappointing moment. not because the mystery had become impossible to solve, but because one of humanity's best opportunities to investigate it would have to wait. Science rarely advances in a perfectly straight line. Some missions succeed brilliantly, others fail, some are postponed, others are cancelled entirely. Each generation builds upon the efforts of the last. The search continues, and perhaps that is the most beautiful part of this entire story. When we first looked up at the moon, we imagined a silent world of dry stone. Today we see something entirely different, a place where invisible water may drift quietly across the surface, where ancient comet ice may rest beneath mountains of dust, where microscopic glass beads may gather moisture grain by grain, where hidden freezers colder than Pluto preserve secrets older than life on Earth, where every new spacecraft returns with answers and even better questions. If humanity eventually learns how to find, understand, and responsibly use this hidden water, the consequences will reach far beyond the moon itself. Future explorers may refuel there before travelling onward to Mars. Scientists may build observatories unlike any ever constructed on Earth. Engineers may develop technologies that allow people to live sustainably on worlds that once seemed forever beyond our reach. Yet perhaps the greatest lesson is quieter than all of those achievements. The moon has been hanging above our world every night for countless generations. Children have pointed toward it. Poets have written about it. Sailors once navigated beneath its light. Astronauts have walked upon its surface. And after all these centuries of observation, our closest neighbour still reminds us that familiarity is not the same as understanding. Sometimes the greatest mysteries are not hidden in distant galaxies or beyond the edge of the observable universe. Sometimes they wait patiently in the sky above our own homes, asking us to look one more time, a little more carefully than before. And perhaps, as you begin to relax and drift towards sleep, there is something quietly comforting in that thought. The moon has not changed very much over the billions of years that it has accompanied our planet. It has simply been waiting for us to ask better questions. With every mission, every careful observation, and every patient discovery, we come a little closer to understanding not only where water hides among its silent craters, but also how humanity might one day take its first lasting steps into the wider solar system. Until then, the moon will continue to rise above the horizon, calm and familiar, carrying its ancient secrets beneath a blanket of dust and shadow, inviting future generations to continue the search. Good night, and may your own journey through the stars be a peaceful one.